Hi everyone, Jeremy from Chem Made Easy. So in today's lesson on mole calculations, we're going to be covering only 4 things. Okay, we're going to talk about relative atomic mass. We're going to cover relative molecular mass. We're going to learn how to calculate percentage mass, and we're going to talk about empirical and molecular formula calculations. Alright, so only 4 things. Okay. So first things first, what is relative atomic mass? Now, relative atomic mass is the average mass of one atom of an element compared to the mass of 1 over 12 a carbon-12 atom. Alright, so it's really a ratio. Okay, so it is the ratio of the mass of one atom of whatever element we have, alright, to 1 over 12 a carbon atom, a carbon-12 atom. Okay, so for example, if for sodium, as you can see here, the relative atomic mass is 23. What this means is that one atom of sodium is 23 times, okay, so one sodium atom, alright, is equal to 23 times 1 over 12 a carbon atom. Alright, so that's what it really means by relative atomic mass. Now, the reason why some relative atomic masses are not whole numbers is because the relative atomic mass is an average. Alright, it's an average of all the masses of the isotopes present. So let's use chlorine as an example. Alright, now if you're given a sample of chlorine, it will typically contain about 75% chlorine 35 and 25% chlorine 37. Alright, so if you take 75% of 35 and 25% of 37, you get 35.5. Alright, so here you're given another work example. Alright, I'm just going to help you through this. If you want to, you can pause the video and then come back. So here you have 4 different isotopes of lead: 204, 206, 207, 208. The relative abundance is 1.5, 24, 22, and 52.5. What is the AR? So if you're going to follow the steps taken in chlorine, which is here, alright, okay, so the AR will be AR of lead will be, alright, we're going to take 1.5 over 100, multiply this by 204. We're going to take 24%, 24 over 100, and we're going to multiply this by 206. Alright, we're going to add that to, alright, 22 over 100, 22% of 207, and you're going to add that to 52.5% of 208. Alright, now if you punch those values in the calculator, what you will get is, you get 207.24. Alright, which gives you 207 to 3 significant figures. Okay. Now, what is relative molecular mass? Okay, so the word from atomic changes to molecular. So relative molecular mass is the average mass of one molecule of an element or compound. Recall you have molecules that are diatomic, like hydrogen, nitrogen, fluorine, so on and so forth, and then compounds like say methane or carbon dioxide, right? And compared to the mass of 1 over 12 a carbon-12 atom. Okay, so it's the same thing. It's now one molecule, alright, it's a ratio of one molecule, alright, to 1 over 12 a carbon-12 atom. Alright, and this is calculated by adding or taking the sum of all the ARs of the atoms present. So what do you mean? So let's take an example here. Alright, here we have nitrogen N2, because nitrogen is 7 and 14. Alright, N2 is basically 14 times 2, which is 28. Water, now hydrogen is 1 and 1, oxygen is 8 and 16. So H2 will be 1 plus oxygen is 16, and you get 18. We're just going to take, and then for hydrogen chloride, chlorine is 17 and 35.5. Okay, so we take 1, which is hydrogen, plus chlorine 35.5, you get 36.5. Ammonia, nitrogen is 7 and 14, so 14 and 1 and 1 and 1, and you get 17. And finally for ethanol, it's C2H5OH, alright, something that you're more familiar with. So it's carbon, and carbon is 12 times 2. You add that to 5 hydrogens, H5, and 1 oxygen and 1 more hydrogen. Alright, similarly, if you punch those values in the calculator, you should get 46. Alright, okay? Now, you might also hear of this term relative formula mass. Alright, so relative formula mass is for ionic compounds, because ionic compounds these do not exist as molecules. Molecules only for molecular compounds, simple covalent molecules. So for ionic compounds, what you may hear is what you call relative formula mass. Alright? And the method is the same. You want to add the AR of all the ions in the substance or in the compound. So for magnesium sulfate, for example, we're going to take magnesium. This is 12 and 24. Sulfur is 16, 32. Oxygen is 8 and 16. Alright, so we're going to take the larger number. Remember, the AR is the number below. It's a larger number. Okay, I'm just going to highlight that so it's easy to see. Alright, and what we're going to do is magnesium is 24 and sulfur is 32 and oxygen is 16 times 4. Alright, okay. So 24 and 32 and 64 gets you 120. Okay. Now in chemistry, this dot here is a bit interesting. I know in math you do dot product, but in chemistry the dot means plus. This means that one iron sulfate, one unit of iron sulfate is combined with 7 molecules of water. Alright, so you add them together. So iron Fe is 56. So we take 56 plus sulfur 32 plus oxygen 16 times 4. Sorry. And remember, you want to add that to water. Now, water is 18, so it's 7 times 18. Alright, and you punch those values in the calculator, you get 56 and 32 and 16 times 4, 64 and 7 of 18. You get 278. Alright, okay? So that's how you calculate relative formula mass. Alright? So we've done relative atomic mass, we've done relative molecular mass, we've done relative formula mass. Now we're going to move on to percentage mass or percentage composition. Alright? Percentage mass or composition is the percentage by mass of an element in a compound. Now, let me give you an analogy first. Okay, so let's assume you have a bar of chocolate bar. Okay, and this bar of chocolate here is 300 grams. Okay, and in the bar of chocolate you have, say, nuts. You have 5 nuts. Okay, 5 nuts. And each nut weighs like, say, 2 grams per nut. Alright? And you ask, what is the percentage composition or percentage by mass of nuts in a chocolate bar? So you take the number of the mass of a nut, 2, multiplied by the total number of nuts, 5, over the total mass, 300, multiplied by 100%. So that's what you would do, and this is how on the back of the chocolate bar you see the ingredients there. That's how they arrive at percentage of nuts. Alright? Now, similarly, for percentage composition for a compound, of an element in a compound, what you will do is you take the number of atoms multiplied by the AR divided by the MR multiplied by 100%. So it's a very similar concept, very similar idea. Alright, so here, if you're asked to calculate percentage of nitrogen in ammonium sulfate, you take the number of nitrogen atoms, which is 2, alright, multiplied by the AR of nitrogen, 14, over the total MR, so that's the whole thing, alright, and then you multiply that by 100%. Okay, so let's try this for copper in copper sulfate. Alright, so I'm just going to help you out by writing the ARs here. Copper is 64, sulfur is 32, oxygen is 16. Okay, so percentage mass of copper is basically, now, copper sulfate is CuSO4. Okay, so if you're not very familiar with chemical formula, go and brush up on that. So there is 1 copper atom in copper sulfate. So we have 64 multiplied by 1. Now the MR of copper sulfate is 64 and 32 and 16 times 4. And we're going to multiply this by 100%. Okay, so if you take 64 divided by 64 plus 32 plus 16 times 4, and you multiply that by 100%, you're going to get 40%. So the percentage composition of copper in copper sulfate is 40%. Okay? Now, let's take a slightly more interesting example. Alright, so here we have copper chloride of an unknown formula. Alright, and we know that the percentage by mass of chlorine is 35.68. Find N. Now, copper is 64 and chlorine is 35.5. Now, the method doesn't change, or rather the formula doesn't change. The percentage composition formula is this. You take the number of chlorine, because percentage by mass of chlorine. So we want to find the number of chlorine, or rather the percentage of mass of chlorine in the compound. So we start by taking the number of chlorine atoms, okay, N, multiplied by AR, 35.5, over the total MR. Now this is 64 plus 35.5 N, and you multiply that by 100%. So this becomes more of a mathematical question than chemistry. Once you're able to form the equation, you should be able to use basic algebra to get the answer. So 35.68 is 35.5 N over 64 plus 35.5 N times 100%. Okay. Now, because of a lack of space, I'm just going to do it right here. Change color. So we get 0.3568 to be 35.5 N over 64 plus 35.5 N. Okay. So if you shift things around, you're going to get 0.3568, 64 plus 35.5 N, 35.5 N. Alright? Now I'm just going to skip a couple of steps because I'm a bit out of space, times 0.3568, 22.8. 22.8352 is equals to, alright, I'm going to multiply 0.3568 to 35.5, alright, and I'm going to bring the number over, so 35.5 minus away that, I get 22.83. I get 22.833 N, and I get N as 1. Alright, okay, so in this case, the value of N is 1. Alright, now work example 6. Alright, now from mass in grams, calculate percentage by mass. So in this case, there is no need to calculate AR because they've already given you masses. So here you ask this, if 196 grams of sulfuric acid contains 64 grams of oxygen, 4 grams of hydrogen, what is the percentage composition of sulfur? So if you know that the total mass is 196, okay, then we can find the mass of sulfur first. So mass of sulfur. We're going to take 196, which is the total mass, minus away the mass of oxygen, minus away the mass of hydrogen. Alright, so 196 minus away 64 minus away 4. This gives you 128. And then the percentage mass of sulfur is 128 over 196 multiplied by 100%. And this should give you 65.3%. Alright, so I've placed answers here and there. Alright, so that's how you calculate percentage by mass or percentage composition of a substance in a compound. Alright, I'm going to move on to the last part, and this covers empirical formula. Okay, so and once we're done with this, there are once again questions on the back you can try. Okay, now empirical formula, it tells you the simplest ratio of atoms in a compound. Alright, so for example, for water, H2O, the empirical ratio is 2:1 because the ratio of hydrogen to oxygen is 2:1. Alright, to give you something a bit more difficult, for this compound here, C2H4, this is known as ethene. Now, the empirical formula is the simplest ratio, so this works out to be CH2. Alright, you just divide every number by the common factor. Alright, one more example, I'm just going to write it on the left side now. So for another example here, we could have, say, let's do C5H10, and this is pentene. Alright, the empirical formula works out to be CH2 as well. Alright, so you just take, you find the common factor in there, which is 5, divide the numbers by 5, and you get the ratio. The simplest ratio of carbon to hydrogen is 1:2. Now, how do you calculate this? Okay, so for example, if you're told that a hydrocarbon has 85.7% of carbon and 14.3% of hydrogen, how do you calculate the empirical formula? Now, first, you must be able to construct this table here. Alright, so this table here has 4 rows. Alright, there are 3 columns in the 4 rows. In the first row, we have percentage, and this is given. In this next row, you have AR, so you've got to look for this from the periodic table, 12 and 1. Now, in the third row, there's this term here known as moles, which I haven't quite covered yet, but for now, we're just going to leave it as moles. And all you want to do is you take the number in the first row, divide by the number in the second row. First row, divide by second row. Okay, so this gives you moles. Alright, and what you want to do next is this. You want to divide both decimals or both numbers by the smaller number, in this case 7.14. So you divide that by 7.14, you divide by 7.14. And what you get is 1:2. Alright, so when you get 1:2, the empirical formula is CH2. So this tells you that for this compound, the ratio of carbon to hydrogen is 1:2. Okay, now if you are given extra information, in this case the molecular mass is 42, what you can then do is you can calculate the actual molecular formula. And we do this by doing 3 steps here. Alright, so we know it's CH2, alright, but we don't know what the base is. We know it's 1 carbon to 2 hydrogen, but we don't know if the actual formula is 3:6, 4:8, 10:20. So what we do is we write it in the bracket times n, and we're going to replace the elements for the AR. So carbon is 12, hydrogen is 1, 12 plus 1 plus 1 gives you 14, and that's how we got the 14 here, alright? And you multiply by n because we don't know what n is, and this is equal to 42. If you take a calculator and divide, you get n as 3. You get n as 3. And therefore the molecular formula is C3H6. Okay? So we're going to try another one here. Alright? So recall, first things first, you want to draw the table. Alright? You must draw the table. And then we have iron chloride. So we have iron and we have chlorine. Alright? Then we have in the first row percentage. So iron is 34.5 and chlorine is, well, the remainder. So you take 100 minus away 34.5. This gives you something like 65.5. In the next row, we're going to write the AR. Alright, so iron is 56 and chlorine is 35.5. In the third row, we're going to find the moles. Alright, and that's just basically first divided by second row. Alright, so we take the number on top, divide by the number below. You take 34.5 divided by 56. You get 0.61607. I'm just going to write that as 5 significant figures. 65.5 divided by 35.5. You get 1.84. 1.8450. Alright? And next, you want to divide both numbers by the smaller decimal. Alright? So I'm going to divide both numbers by 0.616. 0.616. 0707. Alright? So this is 1. And divided by 0.61607 gives me 2.99. And therefore, the empirical formula is FeCl3, because 2.99 is about 3. Now a word of caution, alright? This decimal here must be very, very close to a whole number. Now if you get things like, for instance, if you get things like 1.33, 2.66, you cannot just round down and round up. Alright, it's not the correct answer. So for example, if you get 1.33, you need to multiply it by 3, because 1.33 is about 1/3. Alright, it's 1 1/3. 2.66, same thing, this is about 2 2/3. You want to multiply that throughout by 3. Alright, so just be careful. You can only round up and round down if the final decimal is very, very close to the whole number, 0.9 or 0.0 something. Alright, okay, so just watch out for that. So now we know that the molecular mass is 325. How do you calculate the molecular formula? So what you want to do here is this. You want to write out FeCl3, N is 325. Iron is 56, chlorine is 35.5, multiplied by 3, N is 325. And what we're going to do now is you're going to just divide to find N. 325 divided by the sum of 56 and 35.5. And this gives you, times 3. And this gives you 2. Alright, and therefore, it is Fe2Cl6. That's your molecular formula. Okay? Now, let's do one more last example before we call it a day. Alright, so I've already written out the elements for you in the first row. Alright, what you want to do now is you want to fill in the percentages. So it's always percentage first. So carbon is 40.92, hydrogen is 4.58, oxygen is 54.5. You want to fill in the ARs. Carbon is 12, hydrogen is 1, oxygen is 16. You want to find the mole. Alright, so we just take the top row divided by the bottom row. Okay, so 40.92 over 12 gives me something like 3.41. Hydrogen is 4.58, and 54.5 divided by 16 gets me to 3.406. We're going to divide throughout by the smallest decimal, which is 3.406. I'm going to get 1. 3.41 divided by 3.406 gets me 1.001, alright? And 4.58 divided by 3.406 gets me something like 1.34. Alright? So in this case, as I mentioned earlier on, you cannot round h down to 1. Alright? You will not get it correct. So what you want to do is you need to figure out how to get to the nearest whole number. And if it's a 0.3, I'm going to test this by multiplying by a 3. Okay, so if I multiply by 1.344 by 3, I get to about 4.03. So that kind of works. I'm just going to multiply this by 3. I'm going to get to 4, and this gives me 3, and this gives me 3. And therefore, my empirical formula is C3H4O3. Now, you want to be very careful about this, alright? Once again, word of caution, do not round 1.34 down to 1 because that's not correct. Okay? Now, and you want to calculate the molecular formula. So you're given the actual relative molecular mass, you want to calculate the chemical formula or the molecular formula. So, similarly, we're going to write, okay, bracket C3H4O3N is 176. Let's just double check that, okay? Carbon is 12, so 12 and 3 and 4 and 16 and 3 multiplied by N gives me 176. So N is, all you're going to do is 12 and 3, which is 36, plus 4 plus 48, and we're going to take 176 divided by that, you get 2. And therefore, your molecular formula or your chemical formula is C6H8O6. Alright? So I hope this has helped you to calculate empirical and molecular formulas, and I'll see you next time.